Today we are going to discuss about the multiprocessor scheduling. So there are two types of multiprocessing. The first one is the asymmetric multiprocessing. In this type, there is a number of processes. Out of that, one processor will act as a master server. So the master server will be taking care of that scheduling decision, then IO processing, other system activities. So the remaining systems will be only taking care of that executing the system's code. In a symmetric multiprocessing, it is also called as SMP. In a symmetric multiprocessing, every processor has to be taking care of its scheduling. Here there are two types of ready queues are there in symmetric multiprocessing. One is the common ready queue. So for all the processor, there will be a only one ready queue. So the processor needs to take the process from that common ready queue. Consider that. So we have a number of processor, for example, core 1 and core 2, etc. up to core n. Okay. So we have a common ready queue here. It having the number of tasks. Okay. For example, T1 to Tn. Okay. So all the processors are sharing this ready queue. The problem here is at the same time, n number of processors or more than one processor can take the same task for processing. So to avoid that, we need to use the locking system. So this is the core 1. So this is the core 2. This is the core n. So to avoid that more number of processor accessing the number of same task at a time, so we have to use the locking technique. So in the common ready queue. So the second technique is each processor having its own ready queue. So each processor are attached with its own ready queue. Consider this. Consider there are three processors we have. So this is core 1, this is core 2, core 2, so this is core 3. Okay, so each processor is attached with its own ready queue. Consider this is the ready queue of processor 1. So C0, this processor, the core 2 is also having its own ready queue, it having the 2 tasks. So like that, the core 3 is also having its own ready queue. So to it having its 3 tasks. Okay. So here there is no problem that more number of cores can access that same task at a time. So whatever the tasks are assigned with that particular core's ready queue, that core can access the task only from that ready queue. Next, multiprocessor, mul- multi-core processor. So in a multi-core processor, multiple computing cores on the same physical chip, that is called as multi-core processor. So multiple processors on same physical chip. Why we need that multi-core processor? Consider that when a processor accesses memory, it spends a significant amount of time waiting for the data to become available, might be because of the cache miss. So the processor spends 50% of its time is for waiting a data. That is called as memory stall. Consider this. There is a process executed by the processor. So this is the timeline. Okay. Consider the C is a consider C is a compute cycle and M is a memory stall cycle. So here the execution is it consists of so first it starts with a compute cycle, then it waits for data memory cycle, compute cycle. Once the data is available, again it enter into the compute cycle. So out of this, so out of that 100% of its execution time, 50% has been spent for memory stall, waiting for data to waiting for memory to get the data. So to avoid that, so we have implemented the multi-threaded processor cores in which two hardware threads are assigned to each core. Consider that. Consider this. Consider this. This is a so timeline. So we have a two hardware thread. Okay. So while the first hardware thread is first it starts the computation. Okay, this is a thread 1, thread 2. Once they enter into the memory cell, the second hardware thread is allocated to a CPU. Then it starts its computation. Once this memory stall has been over, so that processor, that hardware thread is entered into a memory stall. So the process, these two threads mostly make the processor to available to keep the CPU always busy. Okay. Now consider that chip multi-threading from the processor point of view. So the chip multi-threading is consider we have a four cores, each core having its own two hardware thread. So consider this is a processor. So inside the processor we have a four core, each core having its this is the core 0, each core having its hardware thread. So it's a hardware thread 1. So this is the hardware thread 2. Like that, each core is having the through thread. This from the processor point of view. Okay, so like that, it's a hardware thread 1. So this is the hardware thread 2. So like that, we have a four cores. Okay. So from the processor point of view, there are four cores. Inside each core, there is a two hardware thread. But from the OS point of view, we have a 8 CPUs in total. That is the OS view, operating system view. So operating system view, we have a CPU 0, CPU 1. So we have a CPU 2, CPU 3. So exit up to CPU 8. So here in the chip multi-threading, from the processor point of view, if we have a 4 cores, each core having the 2 hardware thread. Okay, but from the OS point of view, it, each hardware thread will be considered as a one processor. So here in the multi-core processor, we have a two levels of scheduling. So the level one is the software thread. Okay, the level one is the software thread need to be scheduled to a hardware thread. So out of that two hardware thread, if it is a two-core processor, two hardware threads might be there. So out of the two hardware thread, so the software thread need to be assigned to which hardware thread. That is the level one of level one scheduling. In a level two, this hardware thread should be assigned to a CPU. It might be in the round robin fashion mostly. So there are two levels of scheduling. Consider this. So, so this is the level 1. So this is the level 2. Here it is a software threads are getting scheduled here. So these are all the software thread. Next, we have a hardware thread. The next level, these software threads are assigned to, if we have a two core processor, we have a two hardware threads in the each core. So these hard software threads are assigned to this any of these two hardware thread. So this is the hardware thread now. Software thread has been assigned to a hardware threads. This is a level 1 scheduling. In the level 2, that hardware threads need to be assigned to a CPU, that is called as a processing core. Next, so as we have discussed early, so if we have a separate queue attached to separate ready queue attached with the each processor, consider this. So we have a three cores. So core 0, core 1 and core 2. So each processor is attached with its own ready queue. Consider this, there is a ready, this is the ready queue of core 0. So there are 4 tasks are there in the core 0's ready queue. Task 1, task 2, task 0, 1, 2, 3. So like that, the core 1 having its own ready queue, that is it having two tasks T0 and T1. Then the core 2 having it having its own ready queue, it having the three tasks, that is T0, T1 and T2. Now consider all the task execution time are same. You consider it as a, for example, we consider it as a 10 millisecond. So the core to complete all the tasks, to complete the execution of all the tasks which is available in the ready queue of core 0, the core 0 totally need 40 millisecond. But the core 1 need only a 20 millisecond. The core 2 having needs 30 millisecond. So here we have to consider that each task having the 10 millisecond of execution set. Here out of these three cores, the out of these three cores, the core 0 is heavily loaded. Okay, for 40 millisecond it will be busy, but the core 1 will be completed its execution only within a 20 millisecond. So in this time, what we need to do is we have to balance the load among all the cores. So there are two techniques for balancing the load among the cores. The first one is the push migration. In the push migration, there is a specific task periodically checks the load on each processor, and if it finds an imbalance, so it evenly distribute the load by moving the task from one processor heavily loaded core to a lightly loaded core. Whenever it finds imbalancing, so there will be a separate application. Okay, specific task will be periodically checking. Okay, specific task will be checking. If it finds the imbalancing, so it push the task from the highly loaded core to the lightly loaded core. That is called as migration. The second one is the pull migration. Here in the pull migration, the idle processor itself, okay, the idle once for example, okay, the idle processor itself pull the threads from the highly loaded core to itself. For example, consider after 20 millisecond, after 20 millisecond, after 20 millisecond, the core 1 will become idle. Okay, so what it need to do, it check that core 2 and core 3, it having the task in the thread in the ready queue. So what it do, out of the 2, the core 0 is highly loaded. So it pull one thread, it pull the thread from the ready queue of core 0 and it executes. So the once the core becomes idle, it itself pull the thread from highly loaded core to it and it execute. Thank you. So here today we have discussed what is multiprocess scheduling, what are all the two types of multiprocessing, what is multi-core processor, why we need the multi-core processor, what is memory stall. Okay, from the processor point of view, how the multi-core system will looks like. From the operating system point of view, how that multiprocessing system, multi-core processor system will be. So how we are do the scheduling in the multi-core processing. So how we are balancing the load among the uh, multi-core processor.